Semiconductor tech trends favor China in the long term. Yukio Sakamata, a 73-year-old Japanese chip-making business veteran, took a senior vice president position at Tsinghua Unigroup, a leading Chinese high-tech conglomerate affiliated with the renowned Tsinghua University. His role is to oversee the launching of a DRAM memory chip manufacturing business. It looks like a bold decision and perhaps an ill-conceived move, considering the US-China technology rivalry was growing nastier. The US continues to throw one punch after another at Chinese semiconductor makers Huawei Technology and Semiconductor Manufacturing International Corp. (SMIC), making the idea of launching a new chip-making business in China appear daunting. But Sakamoto remains optimistic. We are living in a world where latecomers have a better chance to catch up with incumbent leaders, because semiconductor technology is progressing more slowly today as the smallness of transistor is approaching limits in terms of physics and optics. He's not talking about the near-term conditions for building a new memory chip factory, which are far from ideal. It's uncertain how long Chinese companies will be allowed to import US chip-making equipment and chip designing software. Rather, Sakamoto is talking about the long-term prospects for China to develop its own silicon wafer fabrication skills and technological capabilities for domestically supplying chip-making materials, equipment, and software. History tells us that a technology paradigm shift can create opportunities for emerging players, and Sakamoto is seeing this unfold in the semiconductor sector today. Moore's law remains on the books. It says that the number of transistors in an integrated circuit chip doubles every 18 to 24 months. It was foretold by Intel co-founder Gordon Moore in the 1960s. Until the mid-2000s, the industry kept pace with the law by shrinking the size of transistors and circuits built on a surface of a silicon wafer die. But miniaturization hit a wall about 15 years ago. The size of transistors had shrunk to about 30 nanometers, 30 billionth of a meter, measured by the width of a central electrode called a gate. Therefore, the speed of miniaturization slowed. Chip makers have nonetheless kept reducing the number of labeling their latest generations of chips, going from 32 nanometers to 22 nanometers to 14 nanometers and 10 nanometers, 5 nanometers, 7 nanometers, and now 2 nanometers. But these numbers stopped representing actual transistor gate size after the mid-2000s, becoming something like brand labels. For example, the actual gate length of a transistor in a 7nm logic chip made by TSMC was somewhere around 18 nanometer, according to University of Tokyo professor Toshiro Hiramoto. It is a stark deviation from the 13 nanometer chips, whose gate length was actually 32 nanometer or smaller. Because of the increased difficulty and rising cost of miniaturization, chip makers are turning to so-called three-dimension technology that make use of the space above the conventional wafer surface to load more transistors onto a chip. For example, the most advanced NAND flash memory chips, NAND flash memory chip, commonly used for data and image storage in smartphones and personal computers, is structured in as many as 96 to 128 layers of integrated circuits stacked on top of the bottom wafer die. While the layers increase and the whole chip thickens, transistor miniaturization has reversed itself in the world of flash memory. Today, the typical transistor size of a flash chip is somewhere in the 22 to 32 nanometer range, larger than the 14 nanometer transistors used in flash memories a few years ago, according to industry experts. Such a shift of importance from miniaturization to 3D technologies is likely to affect the industry's stance about the most difficult part of the chip-making process, photolithography. Photolithography is a process in which a circuit plan is imprinted on the photosensitized surface of a silicon wafer by beaming light toward the wafer through a glass plate called a photomask, on which the circuit plan images are drawn. This is like the traditional photo development process, where an image captured on transparent film is imprinted on paper by projecting light through the negative film toward the photosensitized paper. As circuits further miniaturize, the process needs shorter wavelights for better resolution. The most advanced miniaturization requires invisible light of the extreme ultraviolet or EUV spectrum range. EUV lithography technology is so difficult and costly to develop that all but one lithography machine company, ASML of the Netherlands, have abandoned it. ASML, bequeathed a monopoly, is believed to be selling the EUV lithography machine at a price range of $120 million to $170 million. When a chip maker makes a deal with ASML, it buys a machine that is applicable only to tiny parts of the entire chip fabrication process and which brings about only modest miniaturization effect, industry experts say. EUV machines today are used only for logic chips like PC microprocessors, system-on-chips in smartphone, and graphic processors for games and artificial intelligence data crunching. Because of the complexity of circuit composition, logic chips have not been able to fully deploy 3D layer technologies. When they do, the cost and difficulty of deploying EUV lithography may become less justifiable. Flash memory makers have actually skipped EUV, and DRAM memories are unlikely to require EUV as far as I can see, predicts Sakamoto, who has run DRAM businesses at various companies including Texas Instruments, United Microelectronics UMC of Taiwan, and Elpida Memory of Japan, which today is Micron Technology Japanese plant. If a chip-making plant starts using EUV lithography, it requires many other processes also to be optimized for EUV lithography, meaning massive capital investments for various kinds of advanced equipment. The more advanced the equipment, the fewer suppliers there are, making US bans more effective. But if one can skip EUV lithography, the available choice for chip-making equipment increases. There are more choices for the non-EUV lithography process than EUV. Japan's Nikon and Canon make non-EUV lithography machines. So far, their shipments to Chinese chipmakers have not been blocked by the US. Some Chinese companies, including Huawei Technology itself, have been working hard to develop their own lithography machines. There are reports of successes in making prototypes of a lithography machine using deep-ultraviolet, argon-fluoride, excimer-laser immersion technology, the most advanced among non-EUV lithography technologies. In addition, Yangtze Memory, an affiliate of Unigroup, announced June in 2020 that it had succeeded in developing a manufacturing capability for 128-layer 3D flash memory chips and will start commercial production by the end of 2020. The US seems to have focused on EUV in efforts to block China from obtaining advanced semiconductor technologies. It has been reported that the US successfully persuaded the Dutch government to block ASML from selling EUV machines to SMIC. But as Yangtze shows, China is accumulating know-how in 3D chip making skills, which will eventually be applicable to advanced logic chips and will help the country avoid dependence on EUV-based miniaturization. Of course, there is a harsh reality that most of the non-lithography equipment items handling dozens of chip-making process stages are made almost exclusively by US and Japanese companies. The thin layer deposition process, critical in pursuing multi-layer 3D chip making, is dominated by Applied Materials of the US, and surface inspectors of KLA Tensor of the US are indispensable in completing each such layer. No matter whether 3D tech is involved, if access to US equipment is blocked, it will disable any chip manufacturer in building or expanding its manufacturing capacity. However, in the long run, experts believe China is capable of enhancing its capabilities in all related sectors: materials, optics, chemical, wafer fabrication, process control, surface inspecting, function testing, and so on. Toshiaki Ikoma, former president of Texas Instruments, Japanese subsidiary of former chief technology officer at Canon, was SMIC's chief technology officer in the mid-2000s. Based on his experience there, he believes China has a sufficient number of capable scientists and engineers to develop its own chip-making equipment and chip design software. Their national strategy to send many students to US schools and companies and then repatriate them like a sea turtles, which has been going on for decades, is bearing fruit. Hideki Wakabayashi, a Tokyo University of Science professor, says developing the whole supply chain of chip-making equipment and materials cannot be done quickly, but there is a possibility for China to become a dominant country in the field in 10 to 20 years because of its abundance of talent in all science and engineering fields, he said. And technology trends are a plus for latecomers like China. New technologies such as new materials, 3D, advanced packaging, AI-assist chip design, and cloud-based manufacturing collaboration will all create new opportunities for emerging players, said Samuel Wang, research vice president at Gartner. James Lewis, senior vice president at the Center for Strategic and International Studies in Washington, reminds that a US ban on satellite components to China led non-US companies to become alternative suppliers. Overly broad restrictions will harm the US more than China. Sakamoto said he had been impressed when he was chatting with a Chinese business leader earlier this year. He told me that Chinese teacher leaders are now grateful to Mr. Trump for helping them become resolutely determined to develop technologies on our own, Sakamoto said. It may be true that the US tech squeeze has crushed President Xi Jinping's public dream of China supplying 70% of own semiconductor demand by 2025. In 2019, China fed 16% of its own demand according to IC Insight, but the US policy may be raising the longer-term probability of China realizing Xi's dream.